All right, let's get into one of the most beautiful and, honestly, reality-bending ideas in all of physics, de Broglie's hypothesis. This is the story of how a young French prince proposed that everything in the universe, yep, that includes you, has a secret wave face. Now, to get a sense of just how wild this idea was, you've got to picture the world of physics in the early 1920s. And frankly, it was a total mess. Light sometimes acted like a wave, but then other times, like with the photoelectric effect, it acted like a particle, a photon. Physicists were so turned around that Nobel laureate William Bragg joked they were teaching two completely different, contradictory theories of light depending on the day of the week. And this state of chaos really led to a massive question. Was this whole wave-particle thing just some weird one-off quirk of light? Or was it a clue? A hint that nature had this incredibly beautiful, underlying symmetry that nobody had seen yet? And that's when our hero enters the story. In 1924, a young French prince named Louis de Broglie submits his PhD thesis. And tucked inside was an idea so bold, so completely out of left field, that it was about to change physics forever. De Broglie's whole argument came down to this really elegant appeal to pure symmetry. He basically said, look, if light, which we all know is a wave, can act like a particle, well, shouldn't the reverse be true? Shouldn't matter, things we think of as solid particles like electrons, also have a wave side to them? He proposed extending this duality to, well, everything. And he didn't just throw the idea out there. He gave it a formula, the famous de Broglie equation. Now, the really crucial thing to see here is the relationship it spells out. The wavelength is inversely proportional to momentum. That's just its mass times its velocity. And this is the key. The bigger and faster an object gets, the teeny tiny smaller its wavelength becomes. At first, this was just a really cool theory, but it had an immediate and huge payoff. It solved one of the biggest head-scratchers of the time, the bizarre behavior of atoms. You see, Niels Bohr's model of the atom actually worked pretty well, but it was built on these rules that even Bohr himself couldn't explain. He just had to declare that electrons could only hang out in certain specific orbits with certain energy levels. They were basically just rules made up to fit the data, with no real reason behind them. Why those orbits, and not any of the ones in between? De Broglie came along and gave us the reason. He said, stop thinking of the electron as a little planet orbiting the sun. Instead, think of it as a wave. And an orbit can only be stable if that electron's wave fits perfectly around the track, creating what we call a standing wave, just like a plucked guitar string that vibrates in a clean, fixed pattern. So one of Bohr's allowed orbits is simply a path where a whole number of the electron's wavelengths, 1, 2, 3, and so on, fits perfectly. As the wave circles around, it lines up with itself, reinforcing its own existence. And boom! That is why energy levels in an atom are quantized. It's not a rule, it's a feature of the wave. And a forbidden orbit? Well, that's just any path where the wave doesn't line up. It would loop around and start canceling itself out, essentially wiping itself out of existence. The wave just can't sustain itself there. All of a sudden, Bohr's strange rules had a deep, physical, and frankly beautiful explanation. Okay, so this was a huge success. But in science, a cool theory isn't enough. You need cold, hard experimental proof. Could anyone actually detect the supposed wave nature of matter? The answer came incredibly fast. This wasn't some idea that sat on a shelf for 50 years. Just 3 years after de Broglie's thesis, 2 totally separate experiments confirmed it. And only 2 years after that, he had a Nobel Prize. This was a revolution happening in real time. The first proof came from 2 physicists, Davisson and Germer, at Bell Labs. Their experiment was pretty simple, really. They shot a beam of electrons at a crystal of nickel and then put a detector out to see where the electrons bounced off. Now, if electrons were just tiny little balls, you'd expect them to scatter pretty randomly, right? But that is not at all what they saw. Instead, they found a sharp, clear peak of electrons bouncing off at a very specific angle. The atoms in the nickel crystal were acting like a grating, and the electrons were diffracting just like waves, with a wavelength that perfectly matched de Broglie's prediction. This was the smoking gun. And at pretty much the exact same time, G.P. Thomson over in Scotland got the same result with a different method. He fired electrons through a super thin metal foil and saw these beautiful diffraction rings on a photographic plate, patterns that looked exactly like the ones you get from X-rays, which everybody already knew were waves. The evidence was overwhelming. So particles could act like waves. Case closed. But the implications, they were so much bigger. De Broglie's hypothesis wasn't just about little electrons. It was universal. And this wasn't just some quirk of tiny particles. In the years since, physicists have pushed this to crazy extremes. This interference pattern you're looking at, that wasn't made by electrons. It was made by complex molecules called buckyballs, made of 60 carbon atoms. I mean, these things are enormous compared to an electron. And yet, when you send them through one by one, they act like a wave and build up this pattern. Which, of course, brings us to the most obvious question, right? If absolutely everything has a wavelength, why don't we see a bowling ball get all wavy and diffract when it goes through a doorway? Why doesn't the world we live in look like a blurry quantum mess? Well, the answer takes us right back to de Broglie's simple little equation. Remember, wavelength is inversely proportional to momentum, and everyday objects, like a bowling ball, have a colossal amount of momentum compared to one little electron. And because of that, its de Broglie wavelength is, it's just ridiculously, absurdly small, something like 10 to the minus 34th meters. That is a decimal point followed by 33 zeros and then a 1. It's trillions of times smaller than a proton. A wavelength that tiny is completely, fundamentally impossible to detect. Our world looks solid and classical because its quantum waviness is just way too small for us to ever see. So let's just step back and appreciate the incredible legacy of this one idea. This wasn't just some clever insight, it was the seed from which basically all of modern quantum mechanics would grow. You can draw a straight line. De Broglie says particles are waves. That idea elegantly explains Bohr's weird atom. Then, a physicist named Erwin Schrödinger takes this concept of a matter wave and builds a rigorous mathematical framework for it, the legendary Schrödinger equation. And that gives birth to the entire field of wave mechanics. And wave mechanics isn't just some abstract theory. It is literally the operating system for the modern world. Lasers, transistors, the computer chip you're using right now, MRI machines, all of it works because we understand and can control the wave nature of matter. De Broglie handed us the key. But his amazing discovery left us with one more deep, profound, and lingering question. Think about it. A guitar string vibrates up and down. An ocean wave is made of water going up and down. So if an electron is a wave, what exactly is it that's waving? Answering that question, that's what takes us even deeper into the beautiful, strange, and wonderful quantum world.